Hello, I'm Qinglei Cao from RCL of the University of Tennessee. My topic is flexible data redistribution in a task-based runtime system. In many scientific applications, they need to be redistributed for purpose of better data locality, load balance, as well as performance. For instance, in adaptive mesh refinement, each region needs to be refined. Hence, redistribution is always applied on these regions with the goal of better load balance. The question of data redistribution has been proposed for more than 2 decades. Research on redistribution involves not only EPF, but also MPI towards both coarse and fine-grained for many scientific domains, including linear algebra like ScaLAPACK and particle queues. However, first, these approaches usually focus on regular data distributions, the static two-dimensional block-cyclic data distribution on which the dense linear algebra community has been relying for more than 2 decades. Second, distribution is the goal for these studies. In fact, besides distribution, finding the right data size is also a critical step. Meanwhile, changes have been made in program model. For instance, the MPI plus X model is one of the most popular program paradigms for parallel applications to help developers to relieve the burdens of expressing parallelism. However, as the systems grow increasingly complex in core and node count, in the heterogeneity of the computational resources and application sizes, these burdens become increasingly costly. Even a minor amount of system noise and small delays could introduce significant slack in large-scale synchronous applications. The task-based program model has become popular and has proven to be efficient and productive in this regard, as task-based program runtime could help users to efficiently manipulate the complicated low-level heterogeneous resources so that they get the opportunity to focus more on their domain knowledge instead of computer science. So it's interesting to revisit the data redistribution problem in their context and imagine support for more flexible data redistributions in the task-based runtime system. There are many task-based runtime systems like StarPU, Legion, and here we focus on PaRSEC. PaRSEC literally is a generic runtime system for asynchronous architecture where scheduling of fine-grained tasks on distributed many core heterogeneous architectures. There are clear separations of concerns. Compiler optimizes each task class, developer describe dependency between tasks, and the runtime optimizes the dynamic execution. And also there are several concepts. For instance, multiple devices to support heterogeneous architectures, several domain-specific languages to help users to express dependencies, overlap communication and communication, and etc. Hence, in this paper, we propose a flexible data redistribution algorithm which could solve a general data redistribution problem and evaluate this algorithm in a task-based runtime, that is PaRSEC. To our knowledge, this is the first time a general redistribution algorithm has been proposed in task-based runtime was. This figure depicts a general redistribution problem, redistributing a submatrix from source to target with different distributions and tile sizes. Matrix is stored in tile format using the descriptor in PaRSEC. Each color represents a different process, and the rectangle cycle red is a submatrix to be redistributed. There are several features need to be clarified. First, tiles in source and target are rectangle, not specified as square, and tile size are independent redistribution. Second, displacements in source and target could be any points not exceeding the bounds. To solve this general redistribution problem, zooming in one tile in target to catch its source state in source, we split the target tile into 9 parts or segments according to their location in source, that is northwest, north, northeast, west, inner, east, southwest, south, southeast, as shown in the top figure. The figure below shows all possible categories based on the existence of segments, determined by combination of some metric sizes, tile sizes, and location of the target tile starting point in source. All possible cases of general redistribution problems are extensions of these non-categories. For example, the figure above is an extension of the category 8. The sequential algorithm is revealed in algorithm 1, following the idea that for the tiles in target, send or receive segments when remote, or copy segments when local. Remote means on different processes, while local is on the same process. The benefits of this design are that it first is capable for causing fine-grained redistribution problems for tiled or block-based metric partition. Second, it isolates distribution tile size. Actually, it could solve a redistribution problem with absolute flexibility on distribution tile size and displacement. In this way, all possible redistribution problems could be reduced to a combination of these non-segments, and operations on these segments could be considered as tasks, which thus could be efficiently handled by a multi-threaded task-based runtime system. To efficiently implement this algorithm in PaRSEC, we first briefly introduced the program model in PaRSEC. Actually, PaRSEC is a date-centric programming environment based on asynchronous tasks. From the user perspective, it could be considered as a bunch of task classes with the date descriptor that user defined. Task class is a group of tasks with the same purpose, and each task is an execution unit taking a set of input data and generating a different set of output data. The input flow and output flow express dependencies to guide relationship between different tasks. As to the redistribution implementation in PaRSEC, there are 4 task classes: init, send, receive, and finish. For the purpose of the locality, send is local to source tile, while init, receive, and finish reside on target tile. Several runtime level optimizations are proposed to efficiently utilize the network bandwidth so that to get high performance. But here we only focus on the algorithm itself. The figure below presents an example detailing the dependencies between tasks for a simple redistribution problem. Redistributing source, which has 3 by 3 tiles with 2 dim cyclic distribution, to a target which has only 1 tile on process ID 0. There is only 1 tile in target 00, so 1 task in init and finish, while 9 tiles are involved in source, indexing from 00 to 22. Hence, there are 9 correlated tasks in send and receive. Red arrow represents dependence between local tasks, and blue means remote. Double arrows show date or control dependence between tasks. Experiments are conducted on 2 clusters, NaCl and ShareKing2. NaCl is in RCL, includes 66 compute nodes, and ShareKing2 is a query system with more than 6,000 compute nodes. First, we compare our implementation in PaRSEC to that already exists in ScaLAPACK. ScaLAPACK is a high-performance library for linear algebra routines. ScaLAPACK's data format is inherited from LAPACK, but is targeted to distributed memory machines instead. ScaLAPACK only supports redistribution between regular block-cyclic distributions, so we restrict the scope of this evaluation to such distributions. The above figure presents the time to solution of the ScaLAPACK execution, and the figure below shows the speed up of our implementation compared to ScaLAPACK. We can see ScaLAPACK behaves better for small matrix size, especially with a larger number of nodes, because runtime overhead exists in task-based runtime systems like PaRSEC, but not in ScaLAPACK, which becomes increasingly dominant in weak scaling experiments, as the execution time is very small, as shown in the figure above. In fact, small task granite is not the most suitable setup for a task-based runtime system. As the message size grows, the speedup is almost constant on different nodes. And there is no issue for ScaLAPACK on 64 nodes of NACL. Selective factorization is a widely used algorithm to solve linear systems. We use tau dense Stratsky from the plasma and tau low rank Stratsky from low REPL, both using the PaRSEC runtime systems to evaluate benefits and overheads of redistribution. We evaluate two cases, effect of date distribution and effect of tau size conversion. For the effect of date redistribution, we first redistribute the source distribution to a target distribution, execute on this distribution, and then redistribute back. For the effect of tau size conversion is similar. Redistribute from source tau size to target tau size, execute on this tau size, and redistribute back to the source tau size. The left two figures show performance for dense stress factorization. A showcasing a date redistribution maintaining the tau size. The source matrix is 1D block cyclic that does not expose enough parallelism and thus shows poor performance. A much more suitable distribution for this case, known theoretically but also highlighted in the figure, would be 2D block cyclic. The redistribution redistributes from source distribution to target distribution, executes on the Stratsky factorization, and then redistribute the matrix back to source distribution, such that the entire redistribution is transparent to the caller. In figure B, the date distribution is fixed to 2D block cyclic, but 1280 is suboptimal when matrix is small, as it reduces the parallelism and hinders the performance. Similar, the redistribution redistributes the matrix from source tau size to target tau size, execute the Stratsky factorization, and redistribute matrix back to the source tau size. The red two figures show performance for TRR Stratsky factorization. The settings are similar. Figures above for effect of date distribution, and the figure below is the effect of tau size conversion, but showing the benefits and overheads. Benefits is the execution time of source distribution minus target distribution, or the execution time of source tau size minus the target tau size. Overheads is execution time of only calling date redistribution. From these figures, the redistribution can automatically convert the matrix into a more suitable date distribution of tau size, with little overheads and huge benefits, allowing the execution to be unfolded to most favorable setup on the platform, so that domain scientists do not have to anymore to stick with predefined distribution of tau size, and allow a mismatch between the generator and the user to happen. This paper presents a flexible and general redistribution algorithm for task-based runtime system, supporting any regular and irregular distributions. We provide an implementation in the task-based runtime system PaRSEC, and the practical evaluation of implementation shows it can achieve better performance compared with existing tools supporting some level of date distribution ScaLAPACK. Moreover, utilization in real applications highlights great benefits and little overheads in terms of date distribution and tau size, with significant improvement in applications time to solution. To future work, we plan to explore this redistribution algorithm to other runtime systems. And also in the context of PaRSEC, we plan to further reduce the communication overheads and make the redistribution a completely transparent process to hide all overheads related to the redistribution in terms of memory and time to solution. Thanks.